line integrals. Okay, so suppose that you're here at some point, let's say R at A, and eventually you get to this point R of B. And so there's some parameter, let's say time. So at time A, you're at some point here, and at time B, you're at some point here. And at time A to this point at time B, we travel along some curve C. And at every point, at every time, I'm at some point X, Y. Some vector X, Y. And suppose that I can parameterize this point according to some parameter, T, time. So at time T, you're at X and at Y, and you proceed along this curve according to that parameter. We've done this in the past, not only with time, but we've also done this vectorization with arc length S. So first, let me do the line integral. This is also called, in physics, the path integral. And in complex analysis, this is also called the contour integral. Also means something different in physics. So it's the path integral that corresponds to the line integral. Okay, so rather than the path integral, that's motion spaces. Okay, so let F go from Rn to R. This be a scalar field. And let C be a piecewise smooth curve with R being a vector function. From the closed interval A, this smooth curve. And let this be a bijective parameterization of the curve C. Suppose that A is less than B, and that R at A and R at B are the endpoints of this curve C. Then the integral F over the curve C is just equal to the integral from A to B of F evaluated at R times the norm of the velocity. So this is just the speed times dt. Another notation that they use in the book, they actually use several notations in the book. Okay. This is equal to the integral over the curve C of f of x y ds to the integral from A to B of f evaluated at x of t comma y of t times the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared integrated with respect to dt. Let f go from Rn to Rn. Let this be a vector field. Then the integral over the curve C of f dot dr is equal to the integral from a to b of f of r of t dot r prime at t dt. So we can see that it turns out that this is just going to be the exterior derivative of a one form. And so this is equal to the integral. This will be of one form. That's an exterior derivative. The integral over c of f dot dr is equal to the integral over c of f dot the tangent vector ds. So these are all the same sort of thing. It's just more or less concept. Okay, so suppose I have two curves, C1 and C2. And so you're going, first part is C1, and then the second part will be C2. The integral of C1 union C2 of f ds is equal to the integral of C1 f ds plus the integral C2 f ds. Let me do some examples. I have just a few examples. So let's say on page, wait 1 second. Let me get rid of that. Okay, so 1 second. Okay. So let's do on page 1124. Okay, move. Here it is. Okay, on page 1124, in problems 1 through 16, evaluate the line integral where C is the given curve. So we're only integrating. So let's do that. Of, well, x squared plus y squared plus z squared ds, where the curve C is, well, parameterized as follows. X is equal to t, is equal to cosine 2t, and z is equal to sine 2t. So let's do that. So, oh, and oops, I have to have that t, okay, that t is between 0 and 2 pi. Okay, there. Now I can do it. Okay, so first off, let's see what ds is. Well, if you remember, dx squared plus dy squared plus dz squared is ds squared. Okay. So let's figure out, well, dx is just dt. Dy is equal to, well, the derivative of cosine is minus sine. Two t times the derivative of 2t, which is a 2 dt, and dz is equal to derivative of sine is cosine, 2t times derivative of 2t, which is 2 dt. And so, given that, I have that ds squared is equal to dt squared plus 4 sine squared 2t dt squared plus 4 cosine squared 2t dt. Well, cosine squared plus sine squared is 1, so I can combine these to get t squared plus 4 dt squared. And so this just becomes 5 dt squared. And so I have that ds is just equal to rad 5 dt. Okay, good. So now, from there, I have the integral over the curve C of x squared plus y squared plus z squared d theta. Oh, maybe I should have done, let's also do the x squared plus y squared plus z squared. Let's simplify that also. So x squared plus y squared plus z squared is equal to, okay, and so let's just replace x by t, y by cosine 2t, and z by sine 2t. So this is just equal to t squared plus cosine 2t squared plus sine 2t squared. Well, the cosine squared plus sine squared is 1. So this is just t squared plus 1. So now, let's do this. So the integral over the curve C. Now, even though we call it a line integral, we're usually not integrating over a line like we did in Calculus 1. We're integrating actually over a curve. So it really should be called something like a curvilinear integral or something, but line integral is the terminology that everyone uses. So it's integrating over this curve C of x squared plus y squared plus z squared ds. So this is equal to, well, x squared plus y squared plus z squared is t squared plus 1. ds we found was rad 5 dt, and t went from 0 to 2 pi. So this integral is just equal to this. So let's evaluate this. So let's integrate. So this is 1/3 t cubed plus t rad 5 evaluated between 0 and 2 pi. Let's do that. So this is equal to let's plug in 2 pi. So this is 1/3 times 2 cubed, that's 8 pi cubed, plus 2 pi minus 0, if you plug in the 0, times rad 5. Okay, so this is equal to, I can probably factor out a 2 pi rad 5 over 3. And let's see what remains would be a 4 pi squared plus 1. Oh, wait. How stupid can you be? That's okay, here, wait 1 second. I have an error. I have an error. I have a parentheses error. The 1/3 times 8 pi cubed. Okay, so let's, okay, so bring out the 2 and the pi and the rad 5. Okay, so this is over 3, and so this is going to be a 3 here. Okay, so I factor out 2 pi. And so that is your answer. Problems 19 through 22. Evaluate the line integral. The integral over c of f dot dr, where c is given by the vector function r. Problem number 22. F is equal to x times the vector I plus y times the vector j plus xy times the vector k. R is equal to cosine ti, the vector I, sine plus sine t times the vector j. Okay, plus, actually, let me write it this way. Actually, let me write it like this. Plus tk where t is between 0 and pi. Okay. Let's do this. So first off, let me rewrite as a function of t. And so let me replace x by cosine t, y, and maybe I'll just write it this way, by cosine t, y by sine t, x by cosine t, y by sine t. Okay. Next, let's write, dr. Okay, let's get the screen back. There it is. Let's write dr is equal to the derivative of cosine is minus sine t dt. Derivative of sine of t is cosine t dt. The derivative of t is just dt. Okay, and so this is equal to minus sine t cosine t 1 dt. So I have that f dot dr is just, well, let's multiply these. Minus sine times cosine is the minus cosine t sine t, all times dt at the end, plus sine t times cosine t, plus cosine t sine t times 1. And this is times dt. Let me get another page. So this is equal to, so f dot dr is just equal to cosine t sine t. dt. So the integral over c of f dot dr is just equal to the integral of f dot dr is cosine t sine t dt, where t goes from 0 to pi. 2 sine t is sine of 2t. So we're using the fact that sine 2t is 2 sine t cosine t. One of the double angle formulas. The double angle formula for sine. So this is equal to the integral of sine is cosine 2t, and then I've got to divide by 2, evaluated between 0 and pi. Let me just check if that's correct. The derivative cosine would be a minus sign, and then 2t times derivative 2t, which would give me a 2, cancel out one of those, would give me a plus 1/2. So that's correct. So this is equal to, plug in pi, and so you get a cosine of 2 pi, which is just 1, minus the value at 0, which is again another negative 1/4. And so you get, I guess I need, let me just move this down by 1. And I can then say that this is equal to 0. And so I get that this is just 0. Let me give a little bit more terminology that will be useful in the next section, really, but in the next few sections, actually. So let me introduce some of these concepts. A closed form. A K-form omega is said to be closed if the exterior derivative of omega is 0. Exact forms. A K-form omega is said to be exact if there is a K-1 form phi such that omega equals d